Hello again, this is Jerry Pinter and welcome to part 2 of our lecture from chapter 4. In this part, we will talk about Newton's first law of motion. In part 1, we introduced the concept of forces. And remember, a force was anything that pushes or pulls on an object. In this part of the video, we'll talk about Newton's first law of motion. And then in part 3 of this lecture, we will talk about Newton's second and third laws of motion. So let's begin by stating Newton's first law of motion. Before Newton's day, scientists assumed that all moving objects must have a force acting to keep the object moving. Newton realized that this is not true at all and stated his first law of motion. So Newton's first law has two parts. There's a sort of an easy part that's very intuitive and easy to understand. And then there's the second part is a little more difficult and tricky. So let's talk about the easy part first. Newton's first law of motion states that an object at rest remains at rest unless a net force acts upon it. Okay, and we'll do several examples of this in the next few slides, which will explain this concept. The second part of his law of motion, which is not quite as obvious, is that an object moving at a constant speed remains moving at a constant speed unless a net force acts upon it. So let's see what Newton's first law of motion means. So here's a couple of basic examples. So for the first part of Newton's first law, remember it says that an object at rest remains at rest unless a net force acts upon it. So here is our example. We've got a box sitting on a table. All right, now a couple of questions that you can answer here for me. First of all, are there any forces on this box? Well, yes, of course, right? There's weight, the force due to gravity, pulling the box downward, and we have the table pushing the box upward, right? That's called the normal force, which acts upward. So the key thing here is that the weight force down and the normal force up exactly cancel each other. That means the net force on this box is zero. So an object that's at rest, like this box, will remain at rest as long as there is no net force on it. But of course, if we come along and push this box or kick it, up or sideways, any direction, the box is no longer going to remain at rest because now there will be a net force acting on it. So this part of Newton's first law is pretty logical and intuitive. The second part is a little more tricky. Part 2 says that an object moving at a constant speed remains moving at a constant speed unless a net force acts upon it. So let's look at an example of a hockey puck, which let's say the hockey player struck it with his stick, and this puck is now sliding across the ice. Let's look at the animation here. So the puck is just slowly moving across the ice, and we'll assume that the ice is very slippery and there's no friction. So there is no force right now pushing this puck. Obviously, there is weight down and normal force up, but those two forces balance each other. The key thing here is that this puck is moving at a constant speed. That means there's no net force on it. So this puck is moving. There is nothing pushing the puck to the right. Obviously, something had to push the puck to get it started. But once the puck is set in motion, this puck will continue moving in the same direction at the same speed unless something comes along and acts on it. So for example, if we were to come along and kick the puck, either to speed it up or slow it down, or if the puck all of a sudden went on rough ice and experienced friction, then the puck's motion is going to change. But if there's no changes, no other forces acting on this puck, it will continue to move at a constant speed. So let's look at several more examples of Newton's first law. In the first part of this lecture on chapter 4, you learned how to sketch what's called a free body diagram. Remember, that's just a diagram where we represent the object and all of the forces acting on the object. So let's just start with a couple of real basic ones here. So draw a free body diagram for this box sitting on the table. So when you're done with these two examples, go ahead and pause the video, and I would like you to sketch these out. This is good practice for you to do this on your own so that you have some practice without me just showing you how to do them. The second object is a washer here hanging from a string. So I want you to also sketch a free body diagram for the washer in this situation here. So again, please pause the video now and make a sketch of these in your notebook. All right, here are the answers to our first, these last two examples. So for the box sitting on the table, we actually already did this one. We have the weight force pointing down and the normal force of the table pointing up. And by the way, these two forces should be equal and opposite, right? Because there is no net force on the box. It is, we assume that the box is at rest. Therefore, these two forces have to balance each other and they cancel each other. Now for the hanging washer, we have weight force always down, the force due to gravity. And of course, the string here is pulling on the washer. That creates a force called tension, which we will label with a T. So in this picture, the tension force cancels the weight force here. They are equal and in opposite directions. Now notice there is no normal force on this washer because the washer is hanging in the air. It's not touching the ground. So the only upward force here is the tension. Here are a couple more examples for you to practice with. Let's go ahead and run the animation for a ball rolling across the floor, and we're going to assume no friction. So you can think of this like a real smooth, heavy ball, like for example, a marble or maybe a bowling ball would even be a better example. All right, so here's our ball rolling across the floor. We're going to assume that it's rolling at a constant speed, and we're going to assume that there's no friction. For another example down below here, here's the hockey puck again, and this time it's moving to the left. And again, we're going to assume that it's sliding on slippery ice so that there's no friction. So in each of these cases, I want you to pause the video and draw a free body diagram for the ball up here, and then draw a free body diagram for the puck down here. Now notice these two objects are already in motion. Okay, they have already been sent in motion. All right, so here are the answers to the rolling ball and the sliding puck. So for the ball, we have, of course, weight going down, and the floor is pushing up, normal force up, okay? For the puck, it's pretty much the exact same thing. We have weight force, gravity, pointing down, and we have the normal force of the ice pushing up on the puck. Now, here's the important thing for these. Even though both of these objects are moving, there are no horizontal forces present. Remember, we're ignoring friction and wind resistance and things like that. The objects are moving with constant speed, thus there is no net force. So there, even though the ball was moving to the right, there is nothing pushing the ball to the right. The hockey puck was sliding to the left, but there is no force pushing it to the left. This is the key thing with Newton's first law of motion, especially the second part of his first law, which is a little more tricky when it deals with motion at a constant speed. Here's a chance for you to see a couple of interesting short videos. There's the first video you're going to see is on what's a little device, toy. It's a neat device for doing physics demos too. It's called an air puck. And the second video is a do-it-yourself hovercraft you can make from an old CD or DVD disc and a balloon. So go ahead and watch these two videos.
Objects like planets will continue in their state of motion, straight line at constant speed, unless acted on by a force, like gravity, which would bend them into a curve. Now, we rarely see this on Earth because there's always friction acting on the objects, But there are some circumstances in which we can remove friction. One of these situations is dry ice, and another is floating air hockey pucks.
All right, so now that you kind of had a chance to see how the air puck worked in the video, let's go ahead and do an example where you can get some more practice here sketching a free body diagram for either an air puck or a hovercraft. So here, we have again the floor, and here's our air puck or hovercraft gliding across the floor at a constant speed. So go ahead and make a sketch of the free body diagram for the air puck. The next one is shown down here. It's dragging an object across the table with a string. So you can see here we have a box with a string attached to it, and your hand is pulling on the string, and we're dragging this object across the table at a constant speed. So just assume that we're pulling it nice and slowly and evenly as is shown in the animation. And then the last one to practice down here is a spaceship cruising at 17,000 miles per hour through deep space. So here it goes. We're just showing it going over and over. And remember here, we're in deep space, far from the Earth. So go ahead and again, please pause the video and go ahead and make sketches of these three examples, and then you can check your answers. All right, our answers for the last three examples. For the air puck, remember the reason it works is it has some propellers inside of it that force air downward, and that creates a cushion of air underneath the puck. So there's actually an upwards thrust that's provided by the little battery run motors inside there that spin the propellers. So that air pressure creates a lift or a thrust force going up. That is equal to the weight force due to the puck pointing down. Now again, this puck is moving along the table at a constant speed, so there is no horizontal force pushing it to the right or the left. The air only pushes it straight up and eliminates friction because it's not touching the surface. So notice also for the air puck, there's no normal force, because the puck doesn't actually touch the table or the floor. It is literally floating on a thin layer of air. For the problem with the box dragging it across the table with a string, we again have the weight force going down, the normal force of the table pointing up. We have the tension force of the string that was pulling the box to the right, and we have a friction force opposing the motion of the box. So since the box is moving to the right, the friction force points back to the left. And if this box was moving at a constant speed, like we said it was, the friction force here would be equal to the tension force, okay? They are equal, meaning there's no net force, so this box will continue to move at a constant speed, all right? Notice that the tension force is not larger than the friction force, all right? It's actually equal to the friction force. That's why the box moves at a constant speed. This is, again, part of Newton's first law, the second part of it. Now, here was kind of an interesting one. We've got this rocket flying through deep space at a constant speed, cruising at 17,000 miles per hour. Now, why haven't I drawn any arrows, any force arrows on our rocket? Well, because there aren't any. In deep space, there's no gravity, so it has no weight. Obviously, the rocket is floating in space, so it's not touching anything, so there's no normal force. And again, even though the rocket is traveling very fast, it's traveling at a constant speed, right? It's cruising at 17,000 miles per hour. So that means there's no thrust force. There's nothing pushing the rocket forward. So this rocket literally has no forces acting on it at all. The next concept that we need to cover, which really is necessary before we can talk about Newton's other laws of motion, his second law of motion in particular, is the concept of mass. Mass is a measure of how much matter is in an object. It's also a measure of an object's inertia. Inertia is the resistance to acceleration. So in other words, the more mass something has, the more inertia it has, and that means it's harder to get the object to accelerate, okay? So the units of mass are the kilogram, all right? So remember, we're measuring things in this course. We're measuring distance with meters. We're measuring time with seconds. And now we have a new unit called the kilogram, which measures the quantity of mass. And the abbreviation for a kilogram is a kg. I should point out that, kilogram literally means 1,000 grams. So, but we will be working with kilograms, not in grams. Sometimes in the course, we'll have to make a conversion. In other words, if we're given the mass in grams, we will need to convert it to kilograms. What is a kilogram? Well, a bunch of bananas has a mass of approximately 1 kilogram. If you were to place a 1 kilogram mass onto your bathroom scale, it would weigh 2.2 pounds. So that kind of gives you an idea of how much mass 1 kilogram is. Here's a good thought experiment to do. And thought experiments are very important. Einstein famously did many of the experiments in his head because he didn't have equipment at the time or technology to actually perform a lot of his experiments. And we can sort of do the same thing here. Imagine having an empty shopping cart and then another cart here, which is filled with heavy drinks. Notice this thing's full of soda and wine and beer, so it has a lot of mass in it. Now imagine your task is to just take this shopping cart and push it quickly across the store. All right, so it's at rest here. So obviously this light empty cart here is going to be much easier to push and get moving. In other words, you can accelerate it very quickly by giving it a nice firm push. On the other hand, this cart that's jam-packed with heavy items, when you go ahead and push it, it's going to feel very sluggish. It's going to be difficult to push. Now, the interesting thing here is that the difference in effort needed between this push here and this push here is not due to the weight, because weight points down and you're actually pushing horizontally. So weight is not resisting you here. And it's also not due to friction. a little bit of it is, but friction has been minimized with the wheels in the cart. So why is this cart so much more difficult to get moving? Because it has more mass and it has more inertia. And remember, mass and inertia are resistance to acceleration. It makes something harder to get moving. There's often some confusion when dealing with the concepts of mass and weight. And although they are related to each other, they are very different quantities. They are not the same thing by any means. Mass is an intrinsic property, meaning built in or within the object. It depends on how much material is inside the object. And mass, of course, is measured in the units of kilograms. Weight, on the other hand, is an extrinsic property. It's a measure of the force of gravity acting on the object. In other words, if there's no gravity, then an object has no weight. However, an object's mass never changes. An object's mass is the same on the Earth as it is on the Moon, as it is in deep space where there's no gravity. However, that same object has very different weights on the Earth, on the Moon, and in deep space. Weight, by the way, remember, is a force measured in newtons. Now, the relationship between weight and mass is given by the amount of gravity. So weight is actually calculated as mass times g. Remember, g is the acceleration due to gravity. On Earth, g is 9.8 meters per second squared. We will prove this expression, weight equals mg. We'll prove this in part 3 of this lecture later in this chapter. So, if we think about our apple that's falling off the tree, remember we draw a downward force of the gravity acting on the apple, and we label that force as weight. Well, now we can actually calculate how much weight force there is. We just take the apple's mass in kilograms and multiply it by g, which is 9.8. So how much does 1 kilogram weigh? Well, in class, I would show you a couple of types of spring scale. When you step on a scale in your bathroom, it tells you your weight in pounds. Now, pounds are an English unit of force. And of course, in this class, we're using the metric or SI unit system, and we use newtons for force. So this is a special type of scale that reads newtons. So if we were to hang a 1 kilogram mass from this Newton spring scale, we can calculate the weight as mg. Remember, W, weight is mass times g. So the mass in this case is 1 kilogram, and g, of course, is 9.8 meters per second squared. So the weight then is going to be 1 times 9.8, which is just 9.8. And then we have a bunch of units here. We have kilograms multiplied by meters per second squared, because that was the acceleration. So our weight is 9.8 kilogram meters per second squared. Well, we're never going to say all this stuff. All of this stuff together, a kilogram meter per second squared, is by definition a newton. This is the unit of force called the newton. So this object here, this 1 kilogram mass, weighs 9.8 newtons. And on a scale like this, you'll see that it weighs just a little bit less than 10 newtons. This is a little different kind of spring scale. In this one, the pointer just slides up and down as the spring gets stretched. And again, they show what's shown here in the diagram is a 1 kilogram mass hanging from the scale. And again, it reads just a little bit less than 10 newtons. The actual weight is 9.8 newtons. Here's another thought experiment for you to do that will help distinguish the difference between mass and weight. So you've probably seen the really neat videos from the International Space Station, or maybe older videos showing life for astronauts inside the space shuttle when they're in orbit. So here in this picture, we see a couple of astronauts floating around inside with, looks like they have some fruit as well floating around. You can see the woman's hair is floating as well. They're basically since they're in orbit, They are experiencing basically a weightless environment. Okay, there is gravity because they're not that far from the Earth, but in a sense, they're not feeling the effects of gravity because they're in free fall due to their orbit. So we can sort of, in a sense, say that there's no gravity in their environment. They're not feeling the effects of it. So the question is, how hard would it be to lift up and hold one of these astronauts on the orbiting space station? Well, the answer is it would be very easy because they are weightless. In other words, you could pick up this heavy male astronaut here with one finger and hold them over your head with one finger, and it would be effortless. You wouldn't even feel any weight because he doesn't have any weight. He's in a weightless environment. Now, the different question is, how hard would it be to shake this same astronaut on the space station? In other words, if you grabbed him or her by their shoulders and shook them back and forth, what would it feel like? Would it be like shaking a feather because they don't have any weight? Well, no. The answer is it would be very difficult to shake them. In fact, it would feel exactly the same as if you tried to shake them on Earth because they still have the same mass, therefore they still have the same inertia. And remember what inertia is. Inertia is the resistance to accelerate an object. So if you want to try to shake something, you have to accelerate it. You have to speed it up and slow it down and speed it up, back and forth very rapidly. And that is very difficult to do with a massive object like a human body. So this is our last slide of this part of the lecture. Let's go through 4 different example problems that will be similar to what you would see on homework or quiz or exams in this class. The first question is calculate the weight of a person whose mass is 80 kilograms. All right, well, remember that weight is equal to mass times g, mg. So the weight is 80, g is 9.8, and if you multiply those on your calculator, you'll get a weight of 784 newtons. For our second problem, a car with a mass of 1,000 kilograms sits in a parking lot. Calculate the normal force on the car. All right, so let's draw a free body diagram for the car. So the car is represented by this dot right here. So as always, we have weight pointing down, and let's go ahead and calculate the weight since we know how to do that now. Weight is equal to mg, so we have 1,000 kilograms times 9.8 meters per second squared, and that is equal to 9,800 newtons. So that's the weight force. But this car is also, of course, sitting in the parking lot, so the parking lot is pushing up on the car with a normal force. Now, how much normal force is there? Well, remember, we know this car is at rest. It's sitting still. It's not moving anywhere. So the normal force must be equal to the weight force in order for there to be no net force on this object. So the normal force is also equal to 9,800 newtons. For our third problem here, a chandelier's mass is 20 kilograms and hangs from the ceiling by a cable. What is the tension in the cable? So here's our chandelier represented just by this blob or dot right in the middle. Again, we have a weight force pointing down. Weight force is equal to mg, which is 20 kilograms times 9.8, which is 196 newtons. Now, why doesn't the chandelier fall? Well, because it's suspended by a cable that is exerting a tension force pulling up on the chandelier. And by Newton's first law, since the chandelier is not moving, these two forces must be equal and opposite. They must balance each other because there can be no net force on the chandelier. So therefore, the tension force is the same as the weight force W, which is equal to 196 newtons. All right, here's our last problem of this part of the lecture. A woman pushes a 30-kilogram cart at a constant speed of 2 meters per second. Her pushing force is 50 newtons. What is the value of the friction force? Well, let's go ahead and again draw a free body diagram for this situation. Here is the cart shown in the middle by this dot. So we're going to draw, well, let's first include the weight force is pointing down. and we have a normal force pointing up. We're also told that she pushes she pushes the cart with a force of 50 newtons. So I drew that force going to the left. You can draw it in either direction because it doesn't tell us anything about a direction. So P is for her push, 50 newtons. Now, here's the key thing to this. First of all, we know that if the cart's moving in this direction, to the left, then the friction force is pointing to the right. The question is, what is the value? How much force is there from friction? Well, the key piece of information here is that she's pushing the cart at a constant speed. And I don't care how fast it's going, 2 meters per second, 10 meters per second, it doesn't matter. A constant speed, remember Newton's first law, tells us that if the speed is constant, the net force is 0. So if she's pushing to the left with 50 newtons, the friction force to the right must also be 50 newtons. These two forces cancel each other. There is no net force on the cart. Even though it's moving to the left, there is no net force on the cart. It's 0, and that's why it moves at a constant speed. So I hope you got a good sense of what Newton's first law is. We will continue next with part 3 of this lecture, and we'll talk about Newton's second and third laws. Thank you.